Hello and welcome. Today I'm going to introduce electric potential. 大家好，欢迎大家。今天我将介绍电势 which includes electric potential energy. 那它包括呢电势能 electric potential 电势 equipotential surfaces 等势面 and potential gradient 势梯度。First, let's move on to electric potential energy. 那首先我们就开始看看什么是电势能。Let's begin with gravity interactions. 那我们先从重力开始，这种重力的作用开始。That means we will reveal some basic and fundamental concept of work, potential, energy, and conservation of energy, which proved to be extremely useful in our study of mechanics. 那我们先复习一下我们在重力场当中学过的一些非常重要的一些基本的概念，像这个功啊、能量啊、势能啊，以及能量的守恒啊，这些呢，在力学里面被证明都是非常有用的。Next, we'll show that these concepts are just as useful and effective for understanding and analyzing electric interactions. 那么接下来我们将展示这些基本的概念可以有效帮助我们理解和分析这个电场力的相互作用。Let's review the important points from mechanics. You know, the work done by the force of gravity, you move the matter from point A to point B. The work done by the gravitational force equals the gravitational point product of gravitational force and infinitesimal part of, or we see a small part of move along the path. It's also we can write in this kind of form because the vectors point products means you project one vector to another. For example, the angle between these two vectors is phi. So we can write this in the form of a scalar. This is the work done by gravitational force if a matter is moved from point A to point B. Because the gravitational force is conservative, so the work done by the gravitational force always can be expressed in terms of potential energy. 那因为呢，这个力它是一个保守力啊，这个重力是保守力，那它所做的功啊，我们把一个物体从 A 点移动到 B 点呢，它所做的功呢， 我们总是可以把它表达成跟这个势能有关，也就是它所做的功呢，就等于这个势能的变化量的赋值。That means the work done by gravitational force can be represented in terms of potential energy, or the work done by gravitational force represents function in terms of potential energy. Or simply, we find the relation between the work done by gravitational force and potential energy. 那也就是说呢，我们总能把在重力场中，重力这个保守力所做的功呢，它和这个重力势能的变化有一个对应关系。也就是说，重力在重力场中所做的功，它等于势能变化量的赋值。那这种形式呢，我们可以应用动能定理把它写成另外一个形式。We know work energy theorem is that the change of kinetic energy equals the work done by the force. So from above point 2, we know the change of kinetic energy, and we can express it in terms of potential energy. We often write in the form of 那我们由动能定理知道呢，外力对一个物体所做的功呢，等于它动能的这个机械这个动能的变化量。那我们再进一步把它写成下面这个形式呢，它就是表示它的这个机械能是守恒的。That means the total mechanical energy is conserved under these circumstances. 那就是在这种保守力仅仅做功的情况下，我们的机械能是守恒的。From the revision of above, we can safely infer that the electric potential energy is analogous to gravitational potential energy. So we move on to electric potential energy. 那我们实质上就可以做一个很好的类比。那这种重力场当中重力做功的情况，是不是跟这个电场当中电场力做功的情况，它们和这个重力和这个重力势能之间的关系，重力所做的功与重力势能之间的关系，那电场力所做的功与电势能之间的关系，是不是有一个这个对应的关系呢？实质上这个是一个很好的类比。我们先看一个简单的一个电场力在电场中电场力做功的这样一个例子。Let's see a simple example. Energy in a uniform field. Or we see potential energy in the electric potential energy. 那我们先看一个这个电势能在这个均匀场当中的情形。You know, a pair of charged metal plates sets up a uniform electric field. So we give a setup of simple uniform electric field. A pair of plates. For example, the upper plates have positive charges. The lower plate have negative charges. There is a setup of a uniform electric field. For example, its magnitude is, and there is a test charge Q0, a positive test charge Q0. This is point A, this is point B. They are in the coordinate system, for example. This is the axis of X. This is the y-axis. Electric force is the distance between Q0 and the axis X is y, and the distance between the two plates is d. We know the work done by electric force move the particle or the charge from A to B is F times D equals, F equals Q0 times E. Here in this coordinate system or in this reference system, electric force only have y component is equal. Why we have negative sign? Because the direction of F y is opposite to axis y. So we have a good analogy between gravitational force and electric field force. The left is electric field, the right, we know this just like the gravitational interaction near the surface of the Earth. This is the analogy of these two types of force. They have the similar forms. The forces relate to their field and to their fundamental properties of matters. The electric field force relate to charges and gravitational field relate to mass. We know charge and mass is two essential properties of mass, of physics properties, or fundamental properties of matter. 那我们来看这个，在这种均衡场中，如果我们把电荷，比如说从 A 移动到 B 点的话，那么电场力所做的功呢，我们可以表达成 Q0E_D。那我们还可以把它做一个类比，在电场中和在这个重力场中。那么电场力是和这个电荷以及电场强度有关，而重力呢是和它的质量和重力加速度有关。那我们还可以把它这个，因为是一个非常对称的类比，那我们在重力当中呢，我们有重力势能等于那它只与这个位置相关。那这个电势能呢，一样的，它也是指和这个位置相关。那在这里呢，我们还当然统一可以把它都写成。那当然 ，of course that the work done by electric force move the charge from A to B is equal to the change of potential or the change of electric potential energy. Negative potential energy change. So we have the same results. We can represent the work done by electric force as a function of electric potential energy. 所以同样的在这里呢，我们看我们把这个电场力在电场中所做的功跟这个电势能的变化，我们就联系起来了。实际上我们也就是说，电场力对电荷所做的功呢，它等于这个电荷的电势能等于它的电势能的变化率，这个变化量的负值。所以这个我们是跟我们在重力场当中，我们有同样的这么一个结论。那我们现在探讨一下这个它所做的功的变化情况跟这个电势能之间的变化，它有存在一个什么样的对应的一个这个变化的规律啊？我们可以探讨一下。So let's discuss the several scenarios about different positions about A and B. 那我们下面看几种情形。一种情况呢，那就是 the first scenario is that if 1A bigger than YB, let's look at the work done by electric force. 1A bigger than B than YB means the charge moves downward at the same direction of electric field and the same direction of electric force. So the work done by electric force is positive。那这时候呢，我们说如果 YA 大于 YB 的话，那么这个电场里它所做的功，因为它这个力的方向和它的位移方向是一致的，所以它所做功的是正。而这时候我们的电势能的变化呢，那我们的电势能它会减小。If YA bigger than YB, because the electric force, the direction of electric force is the same as the displacement or the direction of displacement, so the work done by electric force is positive, and the electric potential energy, if 1A less than YB, then the work is negative. 那如果是 YA 小于 YB 呢，那这个所做的功呢就是负。那对应的 and the electric potential energy will increase. This is the two scenarios for the testing point is positive. For negative test charge Q0, we also have two cases. 那上面呢，我们是这个我们的检验电荷是正的情况下，它的两种情形。那如果检验电荷是负的情况呢？同样呢，我们也是两种情况。如果你的这个 YA 大于 YB， similarly we have two cases. If 1A bigger than YB, in these circumstances, the electric force, the direction of electric force is the same as one axis. At the displacement, the direction of displacement is opposite to y axis. So the work done by this situation, the work done is negative. And the electric potential energy will, and if 1A less than YB, the work done by the electric force will be, in this case, the electric potential energy will increase. Anyway, we in general, if the movement direction is the same as the electric field, the electric potential energy, if the movement direction against the electric field, the electric potential energy increases. 那么在一般情况下呢，我们来判断这个的时候，那就是看你这个电荷的这个运动方向，如果是和这个电场的方向一致，那这时候呢，你的这个电势能一定是降低的。如果是 against， 如果你这个电荷的运动方向 是 against， 如果和这个电场的方向相反了，那么这个时候呢，我们的电势能就会增加。So this is the case of energy of electric potential energy in a uniform field. Let's move to electric potential energy of two-point charges. 那我们接下来来看这个是这个，如果是两个带电粒子之间，它们的这个电势能如何来？我们如何来分析和计算 ？For example, we have two charges. They have different signs. We have one charge, for example, Q is. We have another charge, for example, Q0 is negative. Or we have Q is negative and Q0 is positive. 那我们看这个情形，如果我们有两个电荷或者两个带电粒子一正一负，也就是它们异号的情况下，比如说我们把它由这个 A 点移动到 B 点，比如 A 点在这里，我们所说的这个方向呢，我们都是沿着这个两个电荷的这个连线的方向啊，因为这样我们分析起来比较方便一些，简单一些。我们看，我们比如说这个，我们知道了 two position A and B. We know two positions A and B. Their position we know is that respectively RA, R, and RB. This is the charge of Q. That is the charge of Q0. Q and Q0 have opposite sign. Whether Q or Q0 is one is positive, the other is negative. 那我们看，如果是沿着这个两个电荷的这个径向，或者说是连着它的连线方向，我们把它从 A 位置移动到 B 位置。我们来看一下这个所做的功的情况。So let's look at the scenario that we have two opposite sign of charges. We see the case that if we move the charge from point A to point B, and these 2 points are all in the length of, and these 2 points also along the line of the connection of the 2 charges. All we see all have the same radial direction of 2 charges. 我们来看这个是两个电荷之间的，或者说两个带电粒子之间的这个它们的电势能。 From Coulomb's law, we know that the electric force between these two charges, we all have the direction, the same direction as radial direction. 那我们从库伦定律，我们知道这两个电荷之间所受的力呢，它是沿着它们的这个连线方向，是沿着它们的，也就是说沿着这个径向的。So the work done by the electric force Fr move Q0 from A to B is equal to the position RA to RB, because they have the same direction, so it's easy for us to calculate it. We can easily get that那么我们通过这个，我们很容易计算出来这个电场力，它这个如果我们把这个带电粒子 Q0 从 A 移动到 B 点，它所做的功，我们很容易就可以这样计算出来。那么这个我们很容易就可以计算出来。那么这是在这个沿着它的连线方向运动的情形。If the path is not along the radial direction of Q and Q0, if the path is arbitrary path from A to B, or any path from A to B, we have the general form. So this is the case when the path is not a line, for example, it's in the general case. If this is a general path from A to B, from point A to point B, so the general form is that the work done by the electric field force is equal to so we can get potential energy of the 2-point charges is equal to 4 pi epsilon 0 1 over 4 pi epsilon 0 times the product of the two charges divided by R. Also, by the way, I want to stress that in the conserved field, the work done by the conserved force has nothing to do with the path. It only related to the position of the endpoints. For example, in this scenario, whether you move the test charge Q0 from point A to point B in any different paths. It doesn't matter. The potential energy, the change of the potential energy, all the work done by the electric force only has something to do with positions of endpoints. All we see the work done by electric field force is independent of it goes through. 我们在一般情形下，我们得到了这个，我们也可以得到这个。我们把这个他所做的功跟这个电势能联系起来。那最后我们得到一个一般的形式，在两个带电粒子的情形下，在这种情形下，我们来得到了这个电势能。As a matter of fact, potential energy is always defined relative to some reference point where potential energy is zero. 那我们说呢，这个电势能它是一个这个相对的概念。那么你这个电势能我们总是讲它相对于某一点电势能等于0的情况下，相对于这儿来讲，你的电势能是多少？也就是说，你肯定有一个参照点，我们才能谈这个电势能。也就是电势能它是一个相对的概念，就如同我们在重力场中势能它是一个相对的概念一样。我们总要找零势面相对于这个零势面，你的这个势能是多少？那电势能是同样的道理也是相对于你的零电势能面来讲的，对吧？哪里是零电势？相对于这个零电势，我们的电势能是多少所以它也是一个相对的概念。哪里的电势能等于0？我们是相对于这里来讲的。Now let's graphically show the relation between electric potential energy and position. That means show the function graph of U in terms R. This is the diagram about two charges Q and Q0. They are both positive or negative. That means they have the same signs. Q and Q0, they both positive or both negative. Electric potential energy and R, U and R, we know their diagram, their graph is a hyperbolic curve. That means the electric potential energy is positive. So here I want to stress that electric potential energy is a scalar. It can be positive or negative, determined by charge. The two charges have the same sign or the different sign. They have different sign. For example, Q and Q0, one is positive, one is negative, or one is negative, the other is positive. In these circumstances, U will be negative. That means U less than 0. As R near to 0, U nears to negative infinity. When R nears to infinity, U nears to 0. Here U bigger than 0. As r near to 0, u near to positive infinity. As r near to infinity, u near to 0. Let's give a summary. We give a good analogy between electric potential energy and gravitational potential energy. They have the similar functions to describe the relationship between potential energy and position and certain properties or certain physical properties. They are all conserved force and field. When it comes to gravitational field, the force of gravity is conserved. Mechanical energy is conserved when only gravitational force does work. Also, as for electric potential energy, the electric force is conserved. We only have conserved force done work. It's electrical potential energy plus kinetic energy keeps constant. All they are conserved. Also, we give the method how to calculate electric potential energy in a uniform electric field and under 2-point charges. Let's give an example to illustrate how to use what we have learned to solve practical problems. This is our example 1. We have an alpha particle which have the initial kinetic energy is 9.5 MeV. And by the way, I introduce what is electron volt. Electron volt means 1 electron volt equals to 1.602 times 10 to the negative 19 joule。那我们看一个例子呢，这指的是有一个阿尔法粒子，它的初始时具有的这个机械能呢是它动能呢是 9.5 million electron volt， 或者说一伏，也就是每一个电子伏特。一个电子伏特呢等于 1.0602 乘10的负19次方焦耳的这个能量，也就是这是我们已知的有一个阿尔法这么一个离子，它具有这个初始的动能。那它呢将会 alpha particle which have the initial kinetic energy equals to 9.5 million eV electron volt collides with the lead nucleus at rest。 那么它呢就和我们有一个这 lead 就有一个铅原子呢就有一个碰撞。这个铅原子呢它是 at rest， 那就是说它的这个 the collisions do happen but near misses are common。 就这种碰撞呢的确是会发生，但是接近于这种没撞上或者说是这个有偏差，这也是非常常见的。Suppose the alpha particle is not aimed at the center of the lead nucleus, but has an initial non-zero angular momentum。 那假如说这时候的阿尔法粒子呢，它没有直接对准这个铅原子的中央，而是有一个 非零的这个角动量 of magnitude L equals d0 times b. P is the magnitude of the particle's initial momentum, and B equals 1 times 10 to the negative 12 meters. What is the distance of closest approach? L is angular momentum. First, 那我们看呢，这是告诉我们有一个阿尔法这么样的一个离子，它通常是会这个瞄准这铅原子的中央，它会跟它发生碰撞。但是这种情况呢，也会发生，就是它经常会错过，并没有准确的碰到这个铅原子，而是呢，它不是朝着中心过去，而是有一个角动量，也就是有一个偏角。这个角动量我们描述的是它的这个初始的动量乘上一个距离 b 那就是它有这么一个角度的一个偏差，有这么大一个角动量。那现在问我们这个就是它最接近它有这么一个原来准确碰撞的情况下，它是正中碰，就是发生了这个碰撞。那么如果有一个偏差的角度，它现在这么撞过去，那么它最接近这个铅原子的距离是多少？ So when we look at the physical phenomena or physical problem, we should analyze and essential ideas, properties, and some information from the problem. 那当我们拿到一个物理问题时，我们就要认识它物理的一些现象，认识它物理背后的一些原理、一些规律。那这呢，显然就是它是一个这个 alpha particle. We have a alpha particle which have the initial kinetic energy. 那它有这个初始的动能，也就是有速度。那么就是说明它这个初始的这个 initial momentum 我们是知道的。So we can know the initial moment of this particle. 那当它和这个，因为我们首先要知道这一个牵扯到是我们的这个动能它又有角动能那牵扯到能量。那这里呢，除了初始的动能以外呢，那么到了这个它最接近这个铅原子的时候，它一定也有这个动能，一定也有角动量。那它还会有什么呢？因为这个 alpha particle 它是带电的，所以我们这里也要弄清楚这个 alpha particle 和这个，所以我们这里还得知道 so we also should know the number of electrons in alpha particle and the number of protons on the lead nucleus 82 and the number of electrons in the particle alpha particle is equal to 2. What's the meaning of the number of the electrons in alpha particle? That means it has 2 electrons. It has 2 charges of electron. While in the lead nucleus, it has charges of 82 electron. 那我们这里还要补充说明的是，这个阿尔法粒子呢，它有2个电子，那它的带电荷呢，就是2倍的电子所带的电量。那么这个铅原子呢，它有82个质所带的正电荷呢，就是有82个。那下面他就在问呢，在这种情况下，它最接近这个铅原子的这个距离是多少？它会以多么最小的距离来错过这个铅原子？B 告诉我们，同时呢，他还问我们，当这个 B 又等于 repeat B equals and B equals 10 to negative 14. So first we know about the data and the information this problem given to us, and what is the asked questions. Then we should relate this data and questions to what we have learned. We have know the physical principle laws, definition, and knowledge. What we have learned may be used to solve this problem. 那我们拿到这个以后呢，首先我们是看到他给我们的这些数据，给我们的这些问的我们这些问题，然后我们第一步就要思考这些东西能联系到我们这个物理现象，它是一个什么物理现象？这个物理现象又同哪些规律和我们所学过的一些知识呀、概念呀、定理呀、规律啊这些东西联系起来？那首先呢，我们这里要说的呢，就是你拿到这个物理现象要看到它是一个什么样的物理现象。首先呢，它是两个带电的粒子，它们之间又存在着这个位置的变化。这个位置的变化呢，它会牵扯到什么东西的改变呢？势必会发生的是什么在改变呢？它的动能，或者说角动量，它的动量在改变。它的这个还有什么在改变？那我们说这个，当然这个刚开始这个阿尔法离子呢，它跟这个铅离子碰撞以前呢，它的距离是足够远的。这个足够远的意思呢，就是我们对于它们之间的这个存在的这个电势能是在初始状态是可以不考虑的。但是当你这个以这么一个初始的角动量飞向这个铅原子的时候，当你接近它的时候呢，这个距离呢，问我们最近的这个距离的时候，我们一定会考虑它的电势。实际上这个问题我们初始一看呢，它牵扯到的问题呢，它就是两个带电粒子在这么一个电场当中，它只受到这个保守力、电场力的作用。那么这个情况下，我们会联系到什么呢？正如我前面讲的，这些最基本的物理规律、最基本的概念，我们在静力学里面也好，动力学里面也好，运动学里面也好，也就是我们在力学里面所学到的这些最基本的概念，我们如果在满足它的这个条件下，我们完全都可以拿来用。As I have stressed that the fundamental principle laws, the definitions, whatever we have learned in mechanics can be used to whatever the conditions are satisfied. 那就是说我们这些最 fundamental 这些最基本的一些原理、概念、定义、定理、原理都可以用到在它的条件满足的这个情况下，我们全部把它可以用到我们的这个电磁学里面来。这是一个牵扯到保守力，牵扯到这个保守场，那势必我们会牵扯到一些在力学里面我们牵扯到的是机械能守恒。那么在电磁学里面，它的动能加上电势能也是保守的，也是守恒的。This problem is involved a conserved electric force and electric field. Its kinetic energy plus electric potential energy shall keep constant, or they are conserved. Their angular momentum or their momentum also are conserved. 那么这里我们明显的就能分析出来，它的动能加上它的势能，这里面当然指的是电势能，一定是守恒的，那就是保持不变的。同时呢，它的这个角动量或者动量也一定是守恒的。所以这里面呢，我们从这个问题里面呢，我们就说这个 energy and angular momentum。首先我们看呢，它的这个 第一步呢，我们知道它这个初始的。Now first we know the initial kinetic energy is equal the mass of particle alpha times its initial velocity square of its initial velocity. So we can know the square of initial velocity equals 2ke0 over m alpha. First we know the angular momentum is conserved. 首先我们知道呢，角动量是守恒的。Initial angular momentum equals, and the end, if we suppose it is be L1 equals P1. This time the distance become suppose be R. Because P is the initial momentum, so we know L equals L1. P0B equals P1R. That means their momentum mass times velocity. So we know V1 equals B over R times V0. The energy is also conserved. 我们说这个能量也是守恒的。That means the initial electric potential energy plus the kinetic energy equals to the final electric potential energy plus kinetic energy. We know U0 is equal to 0. The initial kinetic energy is 9 mega electron volt. We can write it as 9.5 times 10 to the 6 times E. E represents the E volt. By the way, I want to stress that here we only consider the alpha particle because the lead particle is quite bigger than alpha particle. So when the alpha particle hit or didn't hit the lead nucleus, the lead nucleus particle almost was at rest. 那么这里我要说的是，我们这里实际上只是考虑了 alpha 这个例子，所以我这里还是写清楚一下。因为什么呢？因为 lead always at rest。这里我们说的，它这个铅原子呢，它始终是静止的，你碰撞也好，还是没有碰撞也好，那它始终是静止的。所以这里我们全部考虑是阿尔法粒子这个情况啊，阿尔法粒子在这个时候，它的势能呢，电势能呢，我们写起来就是1 over 4 pi epsilon 0 times. This time we have two numbers of electron, and that means Q and Q0. Q we have number of 2, and we lead nucleus we have number of 82. They all bear the quantity of E charges, so E times E equals E square. The kinetic energy we can express as here R is approaching distance. 当然这里的 R 呢，我们前面应该交代，应该把它放在这里，同样都是 R. We know because we know the relation of V1 and V0, so we replace V1 with their relation. And 2 times 82 is 164. We also know the relation between V0 square and initial kinetic energy. So we plug in V0 with 2ke0 over mR, we get so finally we get equation is that so we can solve this function r equals 2.36 times 10 to the negative 13 plus or minus square root when b equals 1 times 10 to negative 12, we get r equals, and when b equals 1 times 10 to the negative 13, we get r equals, when b equals 10 to the negative 14, we get r equals. Next, we will move on to electric potential. 那接下来我们来看电势。Just as electric field is the force of per unit charge, electric potential is the electric potential energy per unit charge. 就如同我们前面学过的，电场是单位电荷所受的力量。我们的这个电势呢，它也是指的单位电荷的电势能。So we can get the work done by unit charge move from A to B is, this is the potential difference between 2 points, which we can call it voltage. So voltage is the difference between 2 points. The potential. 所以这个呢，我们就可以得到单位电荷它所做的功跟这个电势能之间的关系，进而我们可以推导出单位电荷所做的功呢跟电势相关。那么两点之间的电势之差呢，就是我们所说的伏特。So the concept of voltage, the concept of potential is very, very important for us to understand the electric circuit. 所以我们这个电势的概念以及这种电势这个伏特的这个概念呢，它对我们帮助我们理解电路是非常重要的，它是一个非常重要的概念。So the voltage or the potential of A with respect to B equals to the work done by the electric force when a unit charge from A to B, all in different angle. The potential of A with respect to B equals to the work that must be done to move a unit charge slowly from B to A to against electric force. 那么这里呢，我们就说是 A 点相对于 B 点的电势，它呢就相当于我们这个电场力所做的对一个单位电荷从 A 点移动到 B 点所做的功，或者说我们这个电势呢 A 相对于 B 点的电势呢，它等于我们要把一个单位电荷从 B 点这个移 到 A 点来克服这个电场力所做的功。所以这个从两个不同的角度呢，我们都是可以理解什么是电势。所以这里我们首先要明明确确的知道，电势它是单位电荷的电势能它跟电势能之间的关系。那然后我们又知道了这个电势跟这个电势差，也就是伏特。同时呢，我们知道这个电势它是一个相对的概念，那你就是 A 点相对于 B 点。So from we have learned above, we know for a point charge it is easy. You can easily know the potential equals, or electric potential equals electric potential energy over the charge of Q0. This for a point charge. If it is a collection of point charges, the collection of point charges we have potential equals, we only do is to plus of every individual point charge together. This is the electric potential due to collection of point charges. When it comes to continuous distribution of charges, we can do is that we can superposition them, or we can use integral to describe the electric potential. That means we can divide the charges into infinitesimal or very small parts as delta Q. Then we integrate. We take it as a point charge. Then we use the point charge formula to calculate every point charge, the electric potential of any point charge. Then we integrate it, or we superposition it. We can get the electric potential and electric potential. Also, we can relate electric potential with electric field. So we can find potential from electric field. That is, we know the work done by the electric force moving the charge from A to B from the unit charge, or from charge Q, equals the work is. We know electric force equals to Q0 times E. So the potential difference between potential V, potential A and potential B, point B reference, point A reference, or in terms of point B, equals to. I also want to emphasize that moving with the direction of electric field means moving in a direction of decreasing electric potential, and moving against the direction of electric field means moving in a direction of increasing electric potential. 那我们还要强调的就是，当你这个移动的这个方向同这个电场的强度方向如果一致的话，那它意味着什么？意味着我们在沿着这个电势减小的。那么在一个电场当中，你如果是沿着电场的方向移动的话，那就意味着电势在减小。如果你是沿着电场相反的方向移动的话，那就意味着这个电势在增加。Next, let's look at example 2. Example 2 is about a charged conducting sphere。那我们来看一个带电的一个球状导体，或者说带电球。我们看这种它的这个电势。So we have 比如说我们有一个带电球 ，for example, a charged conducting sphere have radius r, which has positive charge。那我们看一个带电的这个球体，它的电势如何来分析，如何来计算。These problems we have two cases。那这种情况我们有这种带电导体呢，我们分两种情况。一种 one is that when 我们看两种这种位置关系，一种是 when r less than the radius of the sphere. In this scenario, we know the electric field in the conducting body is equal zero. 那么这种情况下，我们知道它的这个在这个导体内部呢，它的电场是等于0的。我们知道这个电荷只能分布于导体的表面，那么在导体内部呢，它的电场是等于0的。So we know inside the sphere its electric field equals 0. That means inside the sphere, no change of the electric potential. In other words, inside the sphere, any point have the same electric potential as it in the surface of the sphere. 那我们就说呢，这时候它内部的任何一个，那我们知道这个，首先我们知道这个，我们前面分析过它这个电场的这种分布情况。那首先我们知道这个，当你小于 r 的时候呢，电场它是0。当你大于 r 的时候呢，我们知道这个电场它是等于1 over 4 pi epsilon 0 times, for example, this has the charge of Q, so Q over R square. So they have the curve like this, hyperbolic curve. 这是我们前面分析过的它的电场的情况。所以这个是什么关系呢？它就是这个电场和这个径向的这个距离的这个关系。那么这种情况下，电势是什么呢？电势我们就知道它是这个4派 epsilon 0分之1乘上一个 Q over R. When R bigger than the radius of the sphere, electric potential equals when R less than the radius of the sphere, the electric potential is constant. When it's bigger than the radius of the sphere, the electric field will change with the distance. Here we have the constant 所以这两种情况下，我们就清楚当这个半径小于这个球的半径的时候，当这个距离小于球的半径的时候呢，我们的这个电势它是一个常量，它跟这个球内任何一点的电势跟这个表面的这个电势是一样的。这个其实我们也很好解释啊，你如果在这个球内任何一点，如果你说这个电势不是一个常量，有变化的话，那就说明你这个球内它是有电荷的，因为你这个如果不是常量，每一点的这个电势不一样，那势必会有这个电场力的存在，那势必会有这个电子的这个移动的状态出现，那就说明它的电场不等于零，所以这个我们也比较容易理解。The result of the example have a lot of practical consequences. 那么这个例子的结果呢，有很多的实际的后果。那它意味着这个后果呢，我们可以利用它，它也可能会有害。Let's give some examples. One consequence has something to do with the maximum potential to which a conductor can be raised. 其中一个后果呢，那就是它涉及到一个导体通电的最大的，它的电压可以提高到最大值是多少。This potential is limited. 那么这个电压值是有限的。Why? 为什么呢？ Because air molecules becomes ionized and air becomes a conductor, and an electric field magnitude of about 3 times 10 to 6. If the magnitude of electric field is about 3 times 10 to 6, the air molecules become ionized and the air becomes a conductor. That means the maximum potential is limited to the radius of the sphere, or the curvature of the curve, times the maximum electric field. 因为当你这个电场强度大到一定值，大约是3乘10的6次方牛顿每库仑的时候呢，那么这个空气中的分子就会被电离化，它就会被这个激励，那么它就会变成一个导体。所以第一个我们说这个它是我们对一个导体对它进行充电，那么它能提高到最大的这个电压是有限的，它的最大电势是有限的。The causing current and its related glow visible in a dark room called corona. 那么这个引起的电流和相关的这种发光现象呢，这个发光是在一个黑暗的屋子里我们是可以看到的，我们称它为 corona。 这个就是所谓的电晕。我们第二个例子来看，我们就是说这个 The second consequence is that you often see a radio antenna, a metal ball or a small metal ball at the end of antenna. 我们常常看到这个天线的顶端有一个小的金属球，那为什么要设计这个东西呢？ It was designed to prevent corona. 它就是为了这个避免这个电晕现象而设计的。 The third consequence is that we often see the blunt end of a metal lightning rod. 我们会常常看到一个这个避棱这个针的这个避棱针的这个顶端呢，一般都是一个不是那么有尖角的，它都是比较钝化的。Because when there are a large amount of charge built up in atmosphere, for example, when in storm or the similar weather， 那比如说在这个我们说这个在这种暴风雨这种天气下 there are excess charge built up， 那么就会聚集很过量的这个电荷在空气中。As a result, the blunt end will build up a different sign of charge， 那么就会引起这个钝化的这个避雷针的这一端呢，会聚集相反符号的很多的这个电荷。When discharged through lightning bolt, they tend to be attracted to the blunt end of a metal lightning rod rather than to other distractors, which would cause damage。 那么当这个闪电，比如说雷雨天气这种闪电放电的时候呢，这些电就会被聚集在这个避雷针顶端的这个钝化的这个地方呢，它就会倾向于被它去吸引，而不会去破坏周围的一些这个建筑一些结构Okay, let's move on to example 3. 那我们下面看这个例3。An infinite line charge or charged conducting cylinder。 那例3呢是关于一个这个无限长的一个充电的这个线，或者是我们说一个导体的这么一个圆柱体。This example is about the distribution charge. So we can use superposition or integral to find through the electric field to find the potential. 那么这个呢，就是一个所谓的这种电荷在导体这种分布的情况。这种情况我们就用所谓的叠加原理，实际上也就是把这个导体你分成若干小的这样一个足够小的这个部分，那么这个每一个小的部分其实就像一个point charge， 我们就可以把它看成一个带电的这个粒子用前面我们用带电粒子的方法把它算出来，然后再把它整个叠加，一种积分的方法所以这个就是典型的通过积分的方法通过这个电场强度来找到电势。所以说我们这个 VA potential at point A minus and point B equal, because the electric field and R have the same direction, so this equals. We know the electric field equals the rate of the charge divided over 2 pi epsilon 0. We get the result. We cite RB equals R0 and get the result is that in this case, if you cite the infinite far away as a reference point, it's make no sense, because if RB becomes infinite, the potential of it becomes infinite. It makes no sense. So we often set RB equals 0 to a certain quantity or to a certain value. 那么这时候呢，我们如果再取无限远处作为我们的这个电势的这个一个参考点，那就显得没有意义啊。你比如说你这个 RB 你取得无限远处，那这个 RB 无限大，我们的电势也无限大，那这个就失去了实际的意义。This is the case in an infinite line charge. If we specifically see it is in a charged conducting cylinder, if the cylinder have the radius r, we can conclude that V equals when r bigger than r. So we set the surface as the reference point or reference surface. If r less than r, the bigger r, inside the cylinder potential is equal 0. 那我们就可以再看，如果是这么一个圆柱体的话，它的半径如果是 r 的话，当它的圆柱体 y 的话，这个它的电势我们可以得到这样一个表达式。那在这个圆柱体的内部呢，很显然它的电势是等于0的，因为这个在内部，在导体的内部它是没有电场的，没有电场。因为什么呢？这时候我们把这个导体的表面呢设置为就是零式面，作为它的一个这个参考电势的一个面。One, the voltage is 0 because we set the cylinder surface as our reference surface. Okay, let's move to example 4. 那我们下面看这个例4。那么例4呢，我们指的是 a ring of charge。我们这个看的是一个带电环。It have charge Q and the radius of the ring is A. If the distance of A to P is X, what is the potential at the point P? This time also we divide the ring to infinitesimal small parts, and then we integrate it. We know the point charge potential is. So then we integrate it. We know R equals square root of S squared plus A squared. And the integral of delta small q equals q. 那么这个呢，就是所谓的一个带电环，它在距离它的中心 x 这个距离的 P 点，它的电势是多少呢？我们可以通过这个积分的方法把它算出来。Let's move to example 5。我们再看这个例5 ，potential of a line of charge， 带电线的这样一个，它的这个某个点的电势如何来计算？This is a line of charge. We set up a coordinate system or reference system, x or y, and the distribution rate of this line of distribution rate of charge of this line is equal to Q divided to A. Also, we have the simple. We divide the line to many small pieces and then integrate. So, any pieces we can see it as a charged point. 那同样的道理，我们也是用计分的方法，我们可以把这个线呢划分成若干的这个微单元，每个微单元我们都可以看成它是一个带电粒子。那么带电粒子对在 P 点的这个电势呢，我们是有公式的。那我们同样是利用so a small part we can see it as a charged particle. Its potential we can calculate it such as we can get the result. I directly give the result. That's the several examples illustrate how to calculate potential, how to calculate point charged potential, distribution charged conductor. At some point, its potential. 那这些例子呢，都是关于如何计算这个电势的。所以我们关于电势呢，介绍就这么。这个电势以及如何计算电势呢，我们先给出这样一些内容。这里面我想强调的呢，就是电势这个概念非常重要。我们首先要回顾一下，我们学过的电势呢，它是单位电荷的这个电势能，所以电势呢，首先它是跟电势能相关，电势能呢又和这个功相关。我们又把这个电势能我们把电势和这个电场强度又联系在了一起，所以这些基本的概念呢非常重要。那么如果所有的电荷都保持静止，那么任何导体的它的这个表面就是一个等式面。The third point is that when all charges are at rest, the entire solid volume of a conductor is at the same potential. 那我们说，如果所有的电荷都保持静止，那么整个这个导体的这个固体的范围内，它都是处于同样的电势水平。这是非常重要的3个关于等式面的3个重要的结论。Let's see another special case. 我们再看另外一种特殊情况 ，a cavity in a conductor. 那么一个导体内如果有一个洞，我们看一下这种情况。比如说，这是我们的导体面，那这是我们的这个 conductor， 它里面有一个 cavity. This is the conductor which have a cavity. This is the surface of cavity. 那里面有个洞，这是它洞的表面。那比如我们看洞内有一个点，这个 P 点，那这是通过 This is the cross section of equipotential surface through point P. If the cavity contains no charge, every point in the cavity is at the same potential. The electric field is zero. Everywhere in the cavity there is no charge anywhere on the surface of the cavity. 那么如果这个洞内不包含电荷，那么在这个洞内的任何一点，它的电势是相同的，它的这个电场等于0，那么这个洞内的这个面上是不带电的。所以说有一个导体内有一个洞呢，你去触摸这个洞壁呢，你不会触电的。So in the cavity, finally, let's look at the potential gradient. 最后呢，我们来看看这个视梯度。We know the potential at point A minus the potential at point B. We can relate it to electric field. We also can write it as the form of so we have delta V equal minus delta V equals the point product of E and L. If we know E is a vector, we can give a reference xyz, so we can represent E as sum of its three components. I hate the direction of I hate component plus the direction of J hate component and plus the component of K hate. That means XYZ component. And we also can write delta L equals I delta X. Also in a similar form. So we get actually every component of electric field we know it is in vector notation. The following operator is called the gradient of the function of f. 那么在矢量当中呢，下面的符号代表的是这个方程的梯，这个方程 f 的梯度。So we can write E as the gradient of V. So delta V is called the potential gradient. 那我们把这个 delta V 呢就称为所谓的视梯度，这个我们简单介绍一下。那今天的课程呢 ，That's the end of today's class. Okay, guys, see you. Bye bye.